See, working on Twitch. See if it's working on X. Still not working on X. Seems like it kind of is. Okay, I think it's working. All right, now let's check the good old YouTube. All right, YouTube is working. How's it going, John Egan? How's everybody doing? I'm gonna go live here in a second. Good morning, Josh. All right, let's go ahead and get started. Let's announce this session and make it official. All right, welcome to another Hoopo stream. Today we're going to be looking at a paper called MindAgent. This is a paper that comes out of a bunch of different groups here. You got University of California, Los Angeles. I think that's UCLA. You got Microsoft Research in Redmond. Specifically within Microsoft, you got the Xbox team. Xbox is the gaming kind of like platform that Microsoft owns. You also got Stanford University. You got Peking University, Tsinghua University, and you also got this big AI, which I had to look up, but apparently it's a pretty crazy thing. It's a decentralized Beijing Institute for General Artificial Intelligence, non-profit, decentralized, open source AI group. Kind of interesting. Never heard of that before. But anyways, you got people such as Fei Li on here. This is some famous researchers here and some kind of heavy hitters as well. You can actually click on all these individual links here and get all these different people here. So you got Jianfeng Gao, distinguished scientist and vice president at Microsoft Research. So a lot of Microsoft money coming into this. But basically what this paper is about is using large language models in an agent capacity. And we've seen this type of research kind of grow more and more. Things like the Minecraft Voyager paper, some of the robotics papers we've been reading, right? This idea of taking a large language model and then using it as a general purpose agent and deciding what all the kind of accoutrements for that specific agent are it feels like we've discovered a new field of reinforcement learning, and this is, I think, the most promising field of reinforcement learning. How's it going, Luke? So this was pretty cool. Had some cute cats, had some video games, and had humans and AIs kind of collaborating together, right? So you got humans playing in VR with AI companions. You got AIs collaborating with the humans. So very interesting stuff. There's a bunch of other agent papers that have kind of come out. So this is another paper that I considered reading today. This is the rise and potential of large language model-based agents. This is a survey paper. So survey papers are basically, they're not papers that introduce a single experiment or a single kind of algorithm or a single kind of concept. Survey papers are more a survey of the current situation, right? So basically what they do is they'll look at hundreds and hundreds of papers and give you a review of how all those different papers are related, maybe where they're similar, where they're different, and try to kind of categorize. But for this YouTube channel, these are little 2-hour streams, so realistically I can't read a survey paper, right? These are like 80 pages long. So I figured, okay, well, instead of that, why don't I basically read a more narrow paper, and then we reference the survey paper occasionally and see kind of where things go from there. the survey paper comes with this GitHub repo here, LLM Agent Paper List, which contains basically a list of all the different LLM papers that they found for this survey paper. So if you're interested in learning more about agents and LLMs as agents and all that stuff, I would heavily recommend this. Is a huge repository of pretty much every single agent paper that exists to date. All right, and you can find any of the links that I go into for this stream here on this Stream Docs GitHub, which is on my personal GitHub. So this is the agent paper list. This is the survey paper for the agents, and then this is the actual paper that we're going to be reading today, this MindAgent paper. Okay, so let's go ahead and get started. Is there any GitHub where important research papers are listed? Yes, there's lots of different GitHubs. There's this one here for agent papers, of course, but you can find there's other people that try to do this. They try to create these GitHub repos that have a bunch of agent or a bunch of paper lists and paper references. There isn't a single place you can go to find all the best papers, and you don't necessarily want that either, because every place you go to that has papers, they're going to have their own biases in terms of what papers they like, what papers they don't like. So you kind of want to browse a bunch of different sources when you're going out into the world and trying to find what papers you want to read. Here we go, Envisioned Agent Society. This is the picture that they used for the survey paper. You know, any paper nowadays, the picture that you use, that first picture is so important that you got to make it professionally. You know, like obviously these people got some kind of video game animator drawer type person to make them this super nice looking figure for this paper. So professionally made figures for papers to increase virality is an increasingly important part of machine learning research, which is weird, but that's the world that we live in. Okay, so let's dive into this abstract here. Large language models have the capacity of performing complex scheduling in a multi-agent system and can coordinate these agents into completing sophisticated tasks that require extensive collaboration. Right? So large language models, everybody's favorite type of machine learning, sometimes called foundation models as well. They're basically AGI. You know, everybody's kind of dancing around this fact that, oh, maybe it's not real AGI. Real AGI means embodied intelligence, or it means lifelong learning, or basically people have moved the goalpost to what AGI is. But 10 years ago, what we're dealing with here with the language models are AGI. So basically, each little individual LLM, you can combine them together and create these kind of agent systems, which the only way that works is because language models are extremely general and they can kind of learn something on the fly. They can kind of be put in an environment that they've never been exposed in, and then very quickly with just a few iterations kind of learn what to do because they have such a good prior and such a good kind of world knowledge, right? They have common sense almost. Okay, despite the introduction of gaming frameworks, community has insufficient benchmarks. So kind of what they're talking about here is there's not really benchmarks for agents. The LLMs as agents is really, really new. So a benchmark would be basically a test set, an evaluation that you could run to compare your thing versus somebody else's thing. So there really isn't benchmarks for agent-like behavior with language models. Towards building multi-agent collaboration, this is the cool part about this paper, is that you have multiple agents collaborating together that encompasses both LLM and human NPC collaborations. Okay, so collaborating with each other and then collaborating with humans. In this work, we propose a novel infrastructure MindAgent to evaluate planning and coordinating emergent capabilities for gaming interaction. And this is another reason why I think language models are basically AGI, is that they have these emergent capabilities where you can put them in an environment and they will impress you with these capabilities that you could have not predicted that they had beforehand, right? These capabilities are emergent. They just emerge out of the extremely strong kind of common sense that these language models have built from just predicting the next token in huge chunks of the internet. Our infrastructure leverages existing gaming frameworks. So, of course, coming out of this Microsoft Xbox team, you bet that they're going to have some pretty solid people to actually do all the game code. require understanding of the coordinator, collaborate with human players via unfine-tuned proper instructions. This is kind of yet another reason why LLMs are AGI, is because you don't even need to fine-tune them to have a specific behavior. Is these things just come out of the box, right? You can do in-context learning, which means that just within the lifespan of that little language model, and it sees a couple things, it already kind of understands what the next thing is, right? It's not, you don't need to basically fine-tune it on a task-specific data set for a specific game. It just kind of out of the box, zero shot, without any fine-tuning, can kind of learn to play the game with just a couple examples, much like a human does, right? Establish in-context learning on few-shot prompt. Furthermore, we introduced Cuisine World, so I think this is going to be their benchmark that they introduce here, a new gaming scenario and related benchmark that dispatch multi-agent collaboration efficiency and supervises multiple agents playing the game simultaneously. We conduct comprehensive evaluations with our new autometric collaboration score, COS. So this is a new score, right? If you have a benchmark like classification on ImageNet, that was a very basic benchmark, ImageNet. Here you go. The score for this is accuracy. It's how well can you classify images into these different categories, such as dogs and cats and so on. But now they're introducing a new metric, which is collaboration score. Our infrastructure can be deployed into real-world gaming scenarios in a customized VR version of Cuisine World and adapted in an existing broader Minecraft gaming domain. Minecraft, obviously, everyone's favorite benchmark for LLM gaming. I think it probably has to do because you have an API. It's a relatively simple game, but it's also got a very long potential kind of exploration tree. Minecraft is simultaneously both simple, but then also has a lot of kind of fractal complexity where if you craft this, then you can craft more things, and they're all kind of like gated behind this tech tree. So it's a very useful environment for testing kind of the exploration capabilities of agents. We hope our findings on LLMs and the new infrastructure for general purpose scheduling and coordination can help shed light on how such skills can be obtained by learning from large language corpora. And I think this is the infrastructure for general purpose scheduling and coordination. That's kind of what's interesting to me, is that, to me, as I said before, I feel like we're basically heralding a new era of reinforcement learning. So reinforcement learning for many decades was basically this. So this is a presentation from a class in Carnegie Mellon about Markov decision process and reinforcement learning. And this is kind of what I call classic reinforcement learning, right? And this is basically a formal system and way of thinking about agents and systems where you have this basic premise here of an agent takes actions in the environment basically either gives you observations or it gives you an explicit state. It also gives you a reward. There's a reward function. The agent gets rewarded, and then you have these kind of algorithms that slowly over time will produce better actions given the state based on some kind of maximization of the reward. And this is the type of reinforcement learning that people have been doing for decades, right? But I think that we're coming into a new age where, because we have these language models now, which are basically like these little mini AGIs, it's kind of rewriting all of reinforcement learning, right? Because reinforcement learning changes completely whenever this little agent here is basically a little AGI. So because we're kind of rewriting the way that reinforcement learning is working, I think that you're starting to see a kind of erosion of the language and the terminology that is used, and it's kind of evolving and changing, right? So that's one thing that I was noticing here, is that in this MindAgent, you can see how they have some of the similar concepts, right? They have this idea of actions. They have this, so you take an action in the game environment. You can get a state from the game environment, right? Similar to here in the reinforcement learning, the classic reinforcement learning, you have states, you have actions, you have rewards, right? Similar kind of concept, but now you have new things, right? So for example, something that doesn't really exist in the reinforcement learning paradigm is this concept of memory, right? Memory history, agent state history. There's works in reinforcement learning that have things like memory, but it's not within the classic formulation of a Markov decision process. So you're seeing kind of this loop, this control loop is kind of changing as we're going deeper and deeper into this LLM tech tree here. So you have things like the dispatcher, which takes the current state, the environment feedback. You have the prompt, the system prompt. Here you have a trajectory, update the action. So you're seeing more complicated setups here that are kind of going away from the classic RL here, where you have a state, policy, reward function, value function. So policy maps from the state space to the action space. Reward function maps from a state to a reward. And a value function is the total expected reward. Okay. Let's go back to the paper, though. Okay, so here they're going to talk about large language models. They're going to reference a bunch of other papers in large language models. Some research has shown the possibility of using LLMs to generate complex plans for robots and game AI, marking an important milestones for LLMs as generalist intelligence agents. So here you go, them dancing around the fact that large language models are effectively AGI, and we're just too afraid to say that. We would like to further investigate the planning capacity. Specifically, we are interested in planning a multi-agent system, i.e. multi-agent planning. Look at that. Compared to planning for a single agent, which has been extensively studied, multi-agent planning imposes much higher problem-solving complexity due to the exponentially growing action space. Right? So if you have a single agent, the agent maybe has a limited action space. So action space is just the space of all actions. So if you have a little robot like this, right, maybe the robot can move forward, backwards, up, and to the right, right, or something like that. If you have two robots, your action space now just doubled, right, because each robot can move forward, backwards, to the left, and to the right. And if you consider the action space of the kind of the multi-agent system as a whole, it's even more, it grew even bigger, because the one agent can go forward while the other agent goes back, and that's a separate action than one agent going forward and the other agent also going forward. So the action space grows really, really quickly if you have a multi-agent system. The planner has simultaneously controlled multiple agents, avoid conflicts, coordinate them into completing a shared goal that requires sophisticated collaborations. To understand to which extent LLMs can obtain multi-agent planning skills, we first establish a new benchmark, Cuisine World. Okay, so we incorporate this AI agent. We design an infrastructure MindAgent inspired by multi-agent task allocation optimization theories to facilitate LLM multi-agent planning capabilities. Our infrastructure enables LLMs to perform complex coordination and scheduling. We conduct comprehensive evaluations, and they try a couple different LLMs here. They're going to try GPT-4, Claude, and Llama. So this is a team of people at Microsoft Research, so I'm pretty sure they should have kind of access to GPT-4, like the good GPT-4. So hopefully we can get some raw numbers here. Zero-shot multi-agent planning. So zero-shot here refers to that there's no additional fine-tuning, there's no additional examples that are given to the agent. The basically the multi-agent system is just executing out of the box on this new environment in this new task. Powerful pre-trained or capable of scheduling multiple agents. So it seems like they're going to be doing 2 to 4 agents into completing dishes. So this is their Cuisine World, by merely reading a simple game instructions. Planning with advanced prompting. So you're seeing this kind of world of prompt engineering come up here. And we've seen other papers on this channel where prompting is very, very important. It's kind of too sensitive, right? It's not as simple as just, hey, the more information you give, the better they're going to perform. We've seen examples where simple, small prompts can improve the accuracy compared to longer prompts that have a little bit more explanation, right? The good old, I forget what it was, but it was basically like, think about it step by step and have fun or something like that, like something that doesn't make any sense, and it's a very short prompt, and if you add that to your prompt, it'll actually perform better on a task. Adding very few expert demonstrations from different game levels to the prompt, explaining the rationale of certain actions as in chain of thought prompting. So here what they're talking about is they're kind of saying that in a lot of the classic reinforcement learning, there was a kind of a specific type of reinforcement learning that people did called imitation or behavior cloning, where basically you're taking a bunch of state action transitions or trajectories, or basically a human playing a game, and then you're trying to derive from that a policy, right? Some kind of function which is going to be a deep neural network, but you're still constrained to this formulation of a Markov decision process where ultimately you're choosing what action to take based on what state you're in. Whereas here, with these language models, it's a lot more fuzzy. There's no kind of explicit action space, right? The action space itself is kind of fuzzy because it's all in natural language. Providing on-the-fly feedback to LLMs during planning. Generalist potentials. LLMs exhibit great potentials of being generalist multi-agent planner as it has strong generalization. LLMs strong generalization. To coordinate more agents with the examples of fewer agents and adaptation to new game domains like Minecraft. While compared to the canonical domain-specific automated planning system, so domain-specific means it's crafted for a specific task, which is how reinforcement learning has worked for all of time, right? You can take the chess AI that plays chess that was made by DeepMind. It's not going to work at all for any other thing other than chess, right? It literally can't even do checkers because it's not even the same action space or the same state space. So the classic reinforcement learning systems are like extremely fragile to their specific domain and their specific task, versus these language models, you can zero shot them to pretty much any task, any language, or any system, any game. Multi-agent planning can still be bottlenecked by challenging computation cost, context length limitation, non-optimal plans, potential of improving from data without fine-tuning via in-context learning. So again, you don't need to actually push gradients into these language models that are related to something like Minecraft. You literally just add some more tokens into the context or the prompt and then basically performs better. We hope our findings for general purpose scheduling and coordination can help shed some light on how such skills can be obtained by learning from large language corpora. Our key contributions are as follows. We establish a new gaming scenario and related benchmark based on a multi-agent virtual kitchen environment, adopts a minimal text-based game format. I guess this is really the only requirement that agents that are language models have, is that they need to be, you need to figure out a way to make the game text-based. So we saw how in the Minecraft paper, or it was called a Voyager, but the Minecraft game has like an API, so the language model was not interacting in the game the way that you and I interact with the game, where we're looking at an actual rendering of the game and then we're like clicking on keys. The way that these language models interact with Minecraft is they see a log output of what is happening in the game, right? So a text log, and then they basically execute API commands that do things in the game. So I guess that is one requirement for language models that is a little bit limiting, is that they're limited to this text modality. How's it going, Bob? Welcome to the live show. You can ask questions. Making an ideal testbed for emergent multi-agent planning and coordination capacity. We introduced MindAgent, an infrastructure for interactive multi-agent planning with LLMs, which demonstrates the in-context learning and multi-agent planning capacity and brings several prompting techniques that can help facilitate their planning ability, including providing few-shot demonstrations, planning rationales, and environment feedback. Yeah, so this is kind of the part that I'm saying where it's like we're seeing the language and the terminology and the kind of core parts of the reinforcement learning world change, right? Where environment feedback, right? That's kind of the same thing as reward, right? The reward is kind of the feedback that you're receiving from the environment, but now it's more complicated, right? Because your reward isn't just a function that you can evaluate and gives you a number, and then a higher reward is better than a lower reward. That's kind of the simple classic RL formulation, but now your reward can be something more nebulous, right? It can be basically like a paragraph, and sure, you could take that paragraph and do some sentiment analysis and say, is this generally good feedback or bad feedback? But it's so much more nuanced, right? Because it's all text. So everything is becoming fuzzy and everything is starting to change and morph. We conduct extensive evaluations with multiple LLMs and prompting settings on our benchmark. Experimental results confirm the potential on being generalist multi-agent planners in terms of generalizing to more agents. We deploy our system into real-world gaming scenarios and demonstrate its capabilities in human AI interactions. Okay, so here you go. You got multi-agent collaboration here. I actually have my own multi-agent reinforcement learning paper, believe it or not. I don't have very many papers, I'm not like a super fancy researcher, but one of the few papers that I worked on is actually a multi-agent reinforcement learning paper. But it's not cool enough to be referenced here, of course. So here we have a Markov decision process. So that's basically this Markov decision process. And POMDP, this is partially observable Markov decision process. So the difference between an MDP and a POMDP is that in a MDP, in a Markov decision process, the state that's coming here is basically perfect. Versus in a POMDP, a partially observable Markov decision process, there's a difference between the actual environment state and then what the agent observes, right? So the state is only partially observable. And that's kind of true of the real world, right? So in the real world, there is like an environment state, a real world state, and then you're observing only some partial amount of that, which may not necessarily even be the actual true state. And you can pull on that thread deeper, right? I think part of the reason that maybe MDPs and POMDPs are not the right way to think about the real world is I don't think the real world is a perfectly deterministic system, right? I think there isn't a pure environment state. Like there's kind of the famous double slit experiment and the kind of the observation effect. And so I think there's a little bit more to base reality than kind of an MDP, but partially observable MDP is kind of a step in the right direction, I think, where you kind of assume that, okay, there's some partial observability to the actual true state of the environment. There has been a recent shift towards utilizing large language models. I don't know about recent shift. I think it's like a complete rewrite. I think we're basically seeing the beginning of actual reinforcement learning, which now that we have basically large language models or AGI, we have to kind of think of this thing completely differently. And I think that the way that these papers, these agent papers, this agent society, I think this is the last thing that humans are ever going to do, is we're basically going to create these kind of frameworks where these little AGI systems kind of interact with each other and then ultimately build towards creating a larger artificial superintelligence, right? So I actually feel like RL is going to die, and when RL dies, maybe we'll see the end of these kind of the terminology here, the terminology of agent, action, state, reward, environment. Maybe we see the end of that. But you're seeing in this new kind of reimagined reinforcement learning, you're seeing kind of a lot of the same old terminology still there, right? Like acting, agents, planning, solving. Okay. I think there was another figure here. Yeah, so you see similar kind of things going on here. You have, oh no. There we go. You have your environment. Your environment has some kind of state. Your perception of that state. You're observing that state potentially incorrectly or partially. Your brain here, I guess they're calling it brain separate from the agent, right? So the agent now has a brain because the brain has to have things like memory, planning, right? Whereas before, in something like this, the agent doesn't have an external memory that it can go to and then come back, doesn't have this idea of like a chain of thought that it can basically spend some actions just thinking about a thing before it takes an actual action. You have text, tools. This idea of tools as well, that's completely new as well. So classic RL, there's no notion of like, hey, the agent can decide to, rather than take an action in the environment, it can decide to call an external tool former API, an external tool such as a calculator or something, and then receive that external information and then change its internal memory or its internal state, right? So the kind of interesting thing is that as we're moving towards this kind of LLM agent-based work, we're kind of starting to feel like these feel very human, right? Like all of these things are much more human-like than this, right? So it's like we're starting to be able to apply all these concepts and ideas from just humans and how do humans work in a human organization, human societies, and be able to apply that to actual like systems, which is kind of crazy. All right. watch and help task, blah, blah, blah. Previous research, planning. This paper's a little bit long. That's why I'm kind of skimming through here. This is just the related work section where they're basically talking about some previous papers. Numerous games have been deployed. Multi-agent collaborations. One player assumes a dominant role while the other player provides support. Okay. I think you see this in a lot of video games too, where there's basically different roles that you play, right? There's like a healer, there's a tank, there's like specific roles within games. And I wonder if that discovers it, right? If you get these language models to play these games, do they come up with the same roles that humans come up with, right? That'd be kind of interesting. That would be an emergent behavior involving some more than just two agents. While the previously studies have ventured into multitask, more have delved into scenarios where agents must complete multiple distinct tasks using competing resources within a single episode. Our work distinguishes itself. Game settings features a diverse array of tools and task objectives. Okay. The new gaming Cuisine World design and benchmark. Okay, so they go more into their little Cuisine World. So it's a flexible multi-agent game, right? Multiple agents cooking in this little coordinated kitchen. I guess they use Unity for that. It's kind of unusual. I didn't know that Microsoft people used Unity, but I guess they do. Your thinking process is so fast. Maybe, I don't know. I just feel like I've just given so many of these chats that maybe, or so many of these streams that maybe it's fast. But definitely, if you feel like there's things that I say that are worth kind of pulling into, go ask me a question and we can side tangent on that. So here we have different benchmarks for multi-agent systems. And I guess here it's like, is it multitask? Do you have to interact with objects? Are there tools that are available to use? How many agents? Is there collaboration? Is there human in the loop? And is there procedural level generation? And of course, the reason they're going to be comparing is because theirs is going to be the best here, so theirs has every single part of that. What is this? 1,369 agents? Light? What the fuck is that? It's a very advanced system here. Okay. Completing tasks necessitates the use of specific tools. Maximum agents denotes the upper limit of agents. Collaboration, teamwork and collaboration. Human in the loop, can you join the game? And then procedural level generation. Do you have basically, can the environment change? How big is the state space? So here are different actions. So the action space. So again, the action space is basically all possible actions that you can take. And now that we're in kind of a text-based action space, the actions are text descriptions. So it's no longer something in the classic RL world where obviously the worst example of this is something like Grid World. So this is the action space for Grid World. You have 4 possible actions, up, down, left, and right? And the way that this is generally done in reinforcement learning is you can literally, the last layer of the neural network that outputs, or the policy that outputs the action, is kind of like a classification model. And it basically says, okay, given this state, what is the next action? And it's classifying into one of these 4 possible outputs here. So it's literally a classification problem. Is it up, down, left, or right, the next step? So look at how simple. It's literally just a one-hot vector with 4 numbers. Compare that to the action spaces that we have now, which are in text, and they're kind of fuzzy, right? It's a go-to takes different arguments than put. It's like a function, right? Number of tools, distribution over the number of tools and ingredients. So I guess this is in the Cuisine World. You're kind of like combining ingredients together, and then like, I guess it's kind of like if you guys have ever played this game Overcooked. It's like a game that you can play where it's like a multiplayer game where you basically like you're gathering little dishes and you're kind of like putting them together, and you have to like go to the plate table and then grab some stuff from the plate table and then move it into here and then chop up the fruit and then combine things in kind of these specific recipes. But you have to be careful, right? Because it's like you have to, it's a very specific order, right? So you can't just kind of try random actions and get something meaningful. You have to follow the recipe specifically. Hoopo just has advanced caching. Maybe I'm not even fully real. What's a mind agent? A mind agent is just the name of the specific framework or that they use here. So mind agent doesn't have a formal definition. Mind agent is a concept that is introduced in this paper and only really matters in this paper. Here they call infrastructure for interactive multi-agent planning. The word that you should think about is just agent. So agent is a something that takes actions and can observe and do things. It's basically like a little consciousness, if you want to think of it that way. And in this case, each individual agent is a language model, or is composed of multiple language models, right? Because you might have a different language model for the actual choosing the action versus a different language model that organizes the memory and selects from the memory. So each individual agent might actually be multiple different language models with different prompts and different system prompts. Task definition. Interactively evaluate LLMs. Overall, the interactive evaluation can be formulated as a Markov decision process. I still feel like this just Markov decision process is just a bunch of old baggage that we need to get rid of, but it's still there. So you have the state space, S. You have the action space, A, all possible actions, state space, S, all possible states, indicating all the possible schedules. Transition dynamics. Transition dynamics is how does one state lead to the next state. Sometimes you hear this terminology model-based reinforcement learning, and in model-based reinforcement learning, you learn a model of the world, right? So that model of the world will tell you at this state, if you take this action, you end up at this state. So model-based reinforcement learning is very successful in these kind of like physics-based systems, like a cart pole or like a robot that's balancing or something, because you can describe those systems very accurately with equations that describe the dynamics, right? The dynamics of transitions from one state to the next state. But they work less well for more complicated state spaces and action spaces. You have your reward function, which is in the classic MDP formulation, it's coming from the environment. So the environment is basically telling you what your reward is. And of course, you have reward functions, which are designed by the humans. But the reward function, I think, is one of those pieces that kind of needs to go away, because it's not... You can't depend on something external like that. I feel like the reward functions should almost be like this kind of internal evaluation of what you're doing. And then a task instruction space, G. I don't know about that. Although there are multiple agents inside Cuisine World, we adopt a centralized planning scheme. So you have one centralized LLM, and then formulate our game as a single agent and a fully observable decision-making process. So here, fully observable, you can see everything. So chess is a fully observable game. Something like poker is not fully observable because you have to be making decisions, but you don't actually know what the cards that other people have, right? So there's a difference between fully observable and partially observable. State space. So what is the state space in Cuisine World? You have location and agent. Okay, for each entity, the game provides a set of descriptions. A location can be storage. Okay, so it's basically all the different parts of the system, such as serving table, pan, blender. I think it's like each of these little stations here is a location, basically. We offer two descriptions. Inside, indicating what items, and occupy, suggesting location is not being used and cannot be touched. So similar to this kind of API access to Minecraft, which we saw in the Voyager paper, Cuisine World has kind of a similar API access where you can say, what is inside the pan? And it'll tell you. What is at the serving table? Or who is at? Here you go. Here's your at function. So you can say at location agent and get, I guess, a Boolean that'll tell you whether that agent is at that location, whether or not the agent is holding something, and whether or not the agent is operating a tool. So different functions here. Hold, occupy, at. Your action space, given n agent entities, a total of n commands need to be generated. So you generate one command per agent per step. And I think that maybe this is an opportunity here. I don't know if you necessarily need this anymore, right? I don't think you need to generate actions at the same exact speed. I think the different agents can generate different, you know what I'm saying? It's not like you need to be in this global kind of clock speed step process where it's like all the agents execute an action and take one step at the same time, right? I could imagine a situation where it's more kind of real time and like agents kind of operate on their own internal clock. So agents take actions when they're ready to take actions. And if one action takes longer than a different action, then the agents maybe fall out of sync, and that's totally fine, right? Let the agent move to location. Let the agent get a specific item. Put whatever the agent is holding to location and activate. Here's the different actions here, which I think are in this table up here. So go to, get, put, activate, and no op. And one thing that I think is interesting here, and I've been kind of messing around with kind of robots and agent, like just here at home, and the choice of these names, I think, is actually, people aren't necessarily thinking about it too much, but I feel like they should, right? Because much like prompt engineering, much like the exact tokens, the exact words that you put in your prompt have a pretty big effect on the actual performance, I'm pretty sure that the name of these functions is also important, right? I haven't seen a ton of research into that, but what if you, instead of calling it no op, you called it do underscore nothing, right? What if instead of calling it do underscore nothing or no op, you called it sit on your hands or something like that, right? It's like, I don't think people are realizing that the choices of the words and tokens that you use for the action spaces in these agents is actually probably has a much bigger effect than people realize. I don't know. I don't have any data to necessarily prove that. I haven't done that experiment, but it's something that I think about all the time. It's like, why are we choosing these names, right? Why are they just get, right? Or go to, right? Like, shouldn't it be a little bit more longer? Wouldn't you benefit from a slightly longer name that has a little bit more information, a little bit more context? I don't know. Okay, so what are the tasks and the rewards in the Cuisine World? I guess you have tuna sashimi, chopping up some tuna meat. So like, these are the actual like kind of plans that they have to execute. So these kind of recipes where they have to perform these specific set of actions at these specific locations. Game episode with a maximum steps of T. So one level, I don't know if you want to think of it that way, one lifetime maybe is a better way of thinking about it. Basically is a total number of steps T, and all these agents have the same number of steps. They're all kind of running on this same clock. Every T-int steps, we name this a task interval. A new task or dish order will be added. A task will be viewed as completed and removed from the active task list. Okay, so you have this kind of like queue almost, right? That's kind of interesting. I like that. When a match disk, on the contrary, a task will be deemed as failed and removed when it least reaches its lifetime. So this is basically overcooked. Lifetime depends on the complexity of the dish, and details can be found in an appendix. Along with these tasks, the game provides rewards and penalties for certain occasions. Okay. We defer to details. Implementing Cuisine World. So obviously they have... this is the Microsoft Xbox team, so they have some game dev people, so they obviously just built this Cuisine World. And I think the reason they built it is because they didn't want to use Overcooked. This is the game that I'm referencing, but this is made by Ghost Town Games. So obviously this is not Microsoft. They couldn't just use Overcooked. So they're like, hey, Overcooked is a pretty simple game. Let's just get one of these game dev guys to do it for us. So that's what they did. So you have 10 types of locations, 27 types of ingredients, 33 unique dishes. This is not a huge space necessarily, but that's pretty big, you know? It's not like a grid world where there's basically 4 possible actions and even chess, right? Like, what is a chessboard? Is it a 10 by 10? 1, 2, 3, 4, 5, 6, 7, 8. It's 8 by 8, so not very big space. Collaboration score. Okay, so this is their metric for their benchmark. Like to evaluate to which extent the dispatcher can coordinate multiple agents into competing dish orders. Similar to the original Overcooked game, I guess here they are mentioning it. We're particularly interested in this question. Can the dispatcher still coordinate the agents into efficient collaborations with smaller T-int? More dish orders are flooding in. Our hypothesis is the ideal dispatcher should be able to coordinating agents until there is way more tasks than the system can handle. Therefore, we introduce collaboration score. Okay, so you have 1 over M. M is the total amount of tasks. So you're normalizing by the tasks. You have the number of completed tasks. You have the number of completed tasks plus the number of failed tasks. So it's literally just how many tasks did you complete out of all the tasks that are there. And there's 5 tasks. What's up, Boo? Boo. She's meowing. Okay, the actual values of tint depend on the game level, blah, blah, blah. But they're kind of less than 10-ish. An overview of our MindAgent architecture, planning, skill, and tool use. The game environment requires diverse planning skills and tool use. It emits related game information. I like how they say the environment is emitting information. This module also converts relevant game data into structured text format. So you need this kind of ability to take the actual game state, which is this more complicated kind of almost visual modality of like this, right? You actually can see what's going on here. And this is how you're playing it as a human, but they have to turn it into text so the LLM can process it. The main workhorse of our infrastructure is the dispatcher. So I don't like this. I feel like it would have been a lot cooler if each agent was its own kind of standalone, right? Imagine if every single agent had its own internal kind of loop that was running by itself, its own memory, its own kind of observability of the current state, and its own ability to decide what its actions are. It seems like the way that they're doing it here, there's kind of this centralized planner, right? This dispatcher here that coordinates everyone on the same clock and kind of decides what everybody else does. But that's kind of different to me, because now that's more like you have a central agent that's kind of using, it's almost like an agent that controls 2 hands, where each hand is the little cats here, which are the individual agents. So I don't know if I would call this multi-agent, right? Because it's not, yes, you have multiple agents in the sense that they're each little individual bodies and they can perform actions, but I don't call myself a multi-agent system, even though I have 2 hands, each of which can do their own separate thing, right? Because there's one central planner. So I feel like they're not, to me, this isn't necessarily a true multi-agent system. Multi-agent, I feel like there needs to be kind of an independence between the different agents, versus here they're all kind of just pawns of this centralized dispatcher here. Right? The dispatcher is what has access to the memory. These agents don't have access to memory. They don't have their own memory. But, okay, you got Cuisine World. The game info gets turned into text information. So here you have going from agent location, tool state, agent holding, pending dishes, timer. You have kind of Oracle. Perfect knowledge of that gets turned into text. So the dispatcher has a perfect knowledge of the entire game state. Environment state, environment feedback. It also basically has the reward, which is basically the pending dishes and the timer and stuff like that. Gets put into this memory, which I guess is just the history of everything. You have the history of all the agents, you have the history of all the actions taken, and the history of all the feedback received. So this could probably grow out of hand. I could see how this can get a little bit crazy if you have too many agents and the game has been going for too long. So there's kind of a limitation here. If your memory is going to be this explicit, then it's going to grow very quickly. I think that what we saw in some other papers where the memory is more selective, right? So it's not the entire state history, the entire action history. It's like you pick which actions to store, you pick which states to store in the memory so that it doesn't grow out of hand. Or you maybe partition it in such a way that you don't need to look at all of it all the time. But the way that it's formulated here, this would grow out of hand very quickly. You feed those into, I guess, GPT-4, which has some specific prompt, and then that ends up creating your actions, which then get executed by the individual agents, even though I don't really think that they're agents. I think this is the agent. Patterns for the action, extraction, full action names, domain-specific language. And I guess the human actions here, the human gets to play as this little Luigi-looking chef, get fed back into GPT-4 so that it can take the appropriate action. So this is these agents are not aware of the human actions until they basically goes into the dispatcher, and then the dispatcher tells them what to do, because the dispatcher knows about the human actions, but the hands, as I call them, or in this paper they're calling them the agents. Yeah, this is not multi-agent. I've made my mind up. Cuisine World is a game that emulates a virtual kitchen where several robots are commanded to use various cooking tools to prepare as many dish orders. To facilitate collaboration, new orders keep flooding in. LLMs need to properly coordinate these robots to maximize overall productivity. Okay. MindAgent infrastructure. Our first foray is an interactive multi-agent planning. MindAgent adopts a minimalist design for the purpose of demonstrating the emerging capacity of LLMs in scheduling and coordination, while also bringing in exploratory prompting techniques that facilitate better planning and shed some light on future approaches. Okay, tell me about that. That's what I'm interested in. Facilitate, our MindAgent is composed of 3 primary components: the prompt, the current state, and the memory. Okay, so the prompt, you can almost think of that like the policy, right? Kind of fuzzy, but the current state would be your state, and then the memory is, I guess, also part of the policy, right? This is kind of what I'm saying, that the classic MDP terminology is like falling apart under the strain of language models and how good they are. The appropriate tools required. Details of the foundational rules of Cuisine World. These instructions delineate an array of actions the agents can undertake. So basically, you have to put all your actions explicitly in the prompt, right? That's what they're calling the instruction. Inference knowledge, house insights, and helpful hints. When utilized appropriately, these hints can guide agents to sidestep potential errors. Okay, so they have like kind of a bunch of helpful hints. One-shot, step-by-step demonstration of the preparation of a distinct dish. This demonstration spans several time steps, each of which is incorporated as part of the prompt. So these are all within the prompt. So the prompt is kind of growing bigger and bigger. Current state provides a snapshot of the prevailing observations, encompasses the information such as the agent locations, the objects currently in the agent possessions, the tools. So this is the kind of oracle knowledge. Includes optional feedback from the environment triggered when the agent's actions contravene. Memory history archives the interaction history with the environment, specifically chronicles the state of the environment and the state of the agents at every time step. Okay. Employs regular expression matching procedure to distill agent actions from the LLM's textual output. This module is indispensable because on occasion the LLM's output is not clean. Yeah, and this is something that I'm noticing too, just in my kind of experiments on agents, is that the agent, or the language model, can output actions such as this, right? In this action space, it can output put this, but sometimes it's not correct, right? Sometimes the actual arguments aren't correct. Sometimes the name of the function isn't even correct. Sometimes it will hallucinate a new action that doesn't exist. So you need to have this hard-coded kind of regex parser, which cleans the actual output of the action, or the output of the language model, such that you can actually execute it. So that's an important part that is kind of, it's an important part of any large language model in the loop kind of agent system, is this kind of action extraction. I call it like a cleaning the action space. Right now I don't know how to do that other than kind of like a regex with some hard-coded rules, but you can imagine how maybe a language model could be used in this as well to do this kind of action extraction, action cleaning. Utilizes a look-ahead checking mechanism. This module parses the proposed actions, assessing their feasibility. Should be an action deemed inexecutable, the error message is promptly returned. Okay. Let's see this. Infrastructure mechanism. Multi-agent system with a total of n agents. I think they had n equals 4. A sequence of p different tasks. I think they had 4 tasks. And then each task has mp different subtasks. Number of types of tasks are unknown at the beginning of the episode. Are they, though? Because you're literally giving them here in the one-shot demo and the inference knowledge. Right? I don't know about that. I don't know if they're unknown. I think they are known. You're literally writing them in the prompt. The agents needed to complete are designated along with other tasks. Each task has an expiration date. After the expiration time, blah, blah, blah. We aim to find valid and optimal task planning, scheduling, and allocations. We define QPIM and CPIM as quality and cost for allocating Agent I to work on the subtask M for the P task in the episode. The combined utility for the subtask is if Agent I can execute subtask M for the Pth task in the episode, and negative infinity. So a little bit of kind of reward engineering here. All right, as soon as you see that negative infinity, it basically means that you're heavily discouraging not having some amount of utility here, so the agent should be able to be allocated to work on something, even if that thing is very far away. So if you're not working on anything and you're all the way in the corner here, right, that negative infinity is going to kind of beat out anything else. We define the assignment of subtask as Agent I is assigned to subtask M or 0. Okay, so you have this notion of assignment. So we see this in this paper as well, where individual agents are assigned to specific tasks. I think they're calling it reasoning and planning, plan formulation. I don't know where it is, but basically the fact that agents have specific roles and specific tasks, right? And you see that even within human company. Like if you think about a company or a group of humans as a multi-agent system, right? Those humans have assigned tasks, right? You're saying, okay, well, you are a manager and you are an engineer and you are doing this, and like assigning specific tasks or specific domains to individual agents leads to better coordinated action. So maybe this kind of fundamental part of multi-agent systems is you have to assign specific tasks to them. Boo, come here. Just hear her meowing. Can you meow for the microphone? Okay, that was a good meow. Define the execution, maximum time allowed. Okay, I think these are all just like details specific to their little Cuisine World thing here, but UPIM, this is the utility. What is VPIM again? VPIM is the assignment. So utility times assignment summed over all possible tasks, all possible agents, and then what is P? P is all tasks. MP is different subtasks. So you're summing over all possible subtasks, summing over all possible agents, and then summing over all possible tasks. And you're trying to find the V here, or the assignment, that maximizes the utility here. So this feels very much like a reward function. Cat appears and the likes on the video go up. Yeah, the cat is way cuter than I am. That's why the cat is the star of the YouTube channel and the brand, because the cat is just way cooler. Subject to summing over all tasks over all. I don't know why they got rid of this is just weird way to write the summations, but for all subtasks M in the set of all possible subtasks, for all what is P? Sequence in set of all possible sequences. It's just like unnecessary mathematical formalism here. This problem cannot be solved in polynomial time. We tackled this problem by using large language models. So you couldn't actually find an optimal solution with just math. You have to use the fuzziness and the kind of general ability of large language models to solve this. When the agent successfully collects an item, the environment emits a signal. I love this emits. You know, kind of like you can emit a photon, and the environment is emitting a signal. I'm going to start using that. When the dispatcher assigns a different task, rewards are not immediately observable. We borrow sprites from temporal difference learning. TD learning is comes from the classic RL world. Let's see, they probably have TD learning somewhere here. Let's see. Temporal difference, here we go. Temporal difference, Q learning. Do they have the actual formula? Here you have classic RL. You have a state take an action, state, take an action, state, take an action. This is the discounted reward. So the reward at state 0, action 0, plus a gamma, which discounts future rewards, right? Your gamma is usually something like 0.999, which means that, or 0.99, which basically means that the reward in the future isn't as good as the reward in right now or in the current state. Whereas here's the Bellman update. Very classic reinforcement learning objective. Value iteration. Okay, we're getting kind of deep in here. Let's go back. Let's pull up. Due to context length limits, it's infeasible to fit the entire history into the context window. Yeah, this is kind of what I was saying before, where you need some ability to selectively pick from the history, right? Maybe not. Maybe we end up, if we think about a future where we have a billion tokens in the context. If you could prompt a language model with a billion tokens, maybe you can put the entire memory every time, right? But if we don't have a billion tokens in the context, we're going to have to figure out a way to pick only the things that matter, right? So I think there's a missing piece here that we're going to have an additional language model that somehow sorts these, or goes through the history and kind of picks which things are most important. And that kind of happens in our brain too, right? It's we're not, even though we have a very, very big memory, we're not aware of that all the time. We're only aware of some limited subset of the memory that our brain is choosing, and that choice of what memory to kind of keep in our kind of cache is context dependent, right? So if you're playing some kind of some kind of basketball game or something like that, the memory that your brain has access to is probably limited to specific basketball memories or specific kind of motor memories. So I think that's something that this paper could have maybe explored a little deeper on, is this how do you filter the memory in such a way that only relevant memories are given to the actual language model that selects the action, right? Or the policy, as it would be called in classic RL. I think that's something that pretty important potential future research direction. Experiments. We conduct extensive experiments. We first introduce the experiment setting and present an analysis of empirical results. Our experiments focus on addressing the following research questions. How efficiently can the model dispatch multiple agents? Can the model dispatch agents for dynamic on-the-fly goals? How do various components... I still don't like the fact that, to me, the model is the agent. This is just a single agent system that has control over multiple NPCs, right? It's kind of like if you're playing a video game and that the character that you're playing in that video game has a pet, I would call the pet and then the main character one character. I wouldn't call the pet a separate character from the main character, because it's the pet doesn't have its own ability to decide to do its own things. It's just fundamentally part of this larger system. So I don't know, this kind of becomes the Chinese room problem, where it's if you have multiple agents acting inside a system, but externally it looks like it's just one system, does that still count as multiple agents, or is it just one system? Right, so we're kind of seeing this weird kind of hive mind situation emerge here. Can the model dispatch agents for dynamic on-the-fly goals? How do various components of the input prompt influence the model's performance? I think this is huge unexplored area. How do other LLMs perform compared to GPT-4? I feel like this is less interesting to me, because any insight that you draw from this doesn't even matter, because one, you don't have access to GPT-4, so you don't know why it performs worse or better. And once you have GPT-5 and Llama 4, the performance comparisons might completely change. So I think this is less interesting to me than things like this. What extent can the existing methods collaborate with human users, and what's the human perception of collaborating with numerous intelligence agents? I think this is more... These are kind of cool as well, because here you're starting to think about what does it look like in a world where you have kind of, as these guys put it, you have this kind of societies of AIs, right? Where right now, when you go into your Gmail inbox, right, it's just you. You're sitting there and you're reading your Gmail inbox. But like, imagine a Gmail inbox where it's like a society. It's like a little, there's like 10 different agents that one of them is like your work agent, and it reads through all your emails and then makes sure to look at to see whether there's work related stuff. And then whenever you show up at your inbox, it's like, hey, I have some work related stuff to tell you about. And then you have a different agent that's more filtering out spam, and it basically you don't really talk to it that much because all it does is just filter out the spam. So like, how are we as humans going to interact and collaborate and even communicate with kind of these systems that are increasingly complicated and increasingly kind of composed of multiple agents that are interacting with each other? Like, how much of that can you see? How much of the interactions between the different agents do you want to see? I don't know. Do humans want to feel like they're just interacting with one other intelligence, right? Like right now, when you go to ChatGPT is really an ensemble. So really it's more like, I think it's 8, but it's 8 different models that are each kind of ultimately giving you one output. And to you, it feels like you're interacting with one intelligence, but really behind it, there's 8 separate intelligences that are all contributing together to appear as one intelligence. Is that always going to be the case? Or are we going to move into a future where humans want to interact with basically multiple agents, right? So every time I put a prompt in here, like blah, 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 multiple different agents come out. It would say, hey, the scientist agent thinks that this is the answer to your question. The social scientist agent thinks that it's this answer, right? So like, do you want that as a human? Do you want different agents with different flavors giving you slightly different answers? Or do you want just one unified, like, I'm just talking to one thing and I don't want to be aware of the fact that it's really a hive mind and it's really just a bunch of separate little agents that are each doing their own thing? I don't know which one of those it's going to be. All right. Let me drink some coffee here. My throat's getting dry. No yerba mate today. We ran out of yerba mate. Got to drink coffee like a plebeian. Okay, we perform experiments through the OpenAI APIs and Anthropic APIs. Okay. All GPT-4 experiments use the GPT-4 0613, and then all ChatGPT use GPT 3.5 Turbo. Dude, if you're like working at Microsoft Research, why the fuck are you using GPT 3.5 Turbo? Like, come on, guys. Like, you guys have infinite money. You're literally, if you use GPT-4, you get the money. Right? Like, I don't think people understand that, but like, OpenAI's cost is Microsoft's profit. And like, all the other companies do this too. Like, Amazon does this and Google does this too, right? Where really you have different companies. So if you're OpenAI and you say, hey, we spent $10 million on compute, guess who gets to say they got $10 million of profit? Is Microsoft, the Azure cloud division. So I don't know why they need to use GPT 3.5 here. Just use the most expensive one, because every token that you're using is a bigger profit for OpenAI's Azure cloud division. So I don't know why they forced them to use that one. We use Hugging Face inference endpoints for Llama 2 Chat HF. It's interesting. They put Hugging Face into 2 words like that. I think it's just one word. We set the temperature for all experiments to 0.1. We report the average result over 3 episodes. Collaboration efficiency. So this is their metric. So here you have the collaboration efficiency for different agents. Again, collaboration efficiency is basically just how many of the tasks did they complete. So 1 is going to be the highest. It completed 100% of the tasks. And then 0 is going to be the lowest. They completed 0 of the tasks. Right off the bat, I don't like how are these, they're not even the same scale. So you see 0.4 here does not line up with 0.4 here. 0.4 here, so like there's an offset here. This is really fucked up. That's not good at all. That's misleading, because now this is actually higher than this. Okay, so I assume that as you get higher levels, it's more complicated, and largely we can see that 2 agents, actually we don't see any we see here level 2 agents does better than 3 agents. Here we have 4 agents doing better. I'm not seeing any pattern here. I see all 3. The ordering doesn't seem to matter, and it's really weird. Okay, so TLDR, collaboration is not simple. There's kind of weird dynamics there. COS score is the highest when there are 4 agents in 3 cases. More agents will lead to higher collaboration efficiencies. I don't know about that, because look at this. In this one, the 2 agent system does better. I don't know. Performance is generally better when there are more agents. LLM dispatcher can coordinate more agents to execute tasks more efficiently. Or another way to think about it is if you have one agent that has 4 hands, it's better than an agent that has 2 hands. Experiment human and multi NPCs with LLMs. Before starting, a web page introduction to the game is handed. It contains rules and basic controls. Then we randomly assign the playing order. Okay, so you got humans playing this through a web browser, it seems. We collect the number of failed and successful tasks. We record the entire action history of players. Therefore, we can replay action histories. And then the participants complete a survey. Okay, so they're basically playing this game. They have some knowledge of the game, so they read a kind of web page that tells them what the game is and what they're kind of roughly supposed to be doing, and then they play, and then they complete a survey. So that's kind of how it works. Okay, which I think is what we're seeing here. So here you have, for example, in Minecraft, you have this guy here at the top corner. He's like spawning in this world. Obviously, he doesn't know. He's like kind of like holding the controllers really weird. I don't know why he's like holding him like that. They're using a Quest headset, so there you go. And then you can see the different bots that they're interacting with. This is fucking awesome. Like, we need this ASAP. Like, I want to be playing VR video games where the NPCs are controlled by LLMs. Like, I don't know why we don't have that already. I feel like it's relatively easy to integrate, and it'd be pretty cool to do that. Agent performance on different tasks. Okay, so all of these are with GPT-4. You see 2 agents. 2 agents seem better. 4 agents seem worse. Look at this. 93% task completion compared to like 69, 79, and then once you do to like 4 agents, it starts getting way lower than that. Seems like it's harder to collaborate more people, which makes sense because that's also happens in human organizations, right? In a human organization, if you have a lot of people, it's generally harder to coordinate than less people. And that actually, it's like a whole thing in software engineering where the more people you add to a software project, the slower it goes. And it's actually counterintuitive. And if a simple mistake that people make all the time when kind of managing software projects is they just overhire, they just hire more and more people, and then the progress just gets slower and slower because coordinating that many people working on the same project becomes harder and harder. So maybe there's kind of an optimal amount of agents. And maybe there's some kind of underlying truth to that, right? Maybe in this emerging science of multi-agent collaboration, you can define some kind of fundamental relationship between the number of agents, the task, and kind of the optimal completion of that task, right? That's kind of a whole area of research that people could go into now as well, where given a specific task description, how many people is the optimal amount of people to have to complete that task? And what are the optimal roles for that as well, right? I think we were looking at a paper in one of the other streams where, I forget what it was called, but it was basically software multi-agent kind of thing, right? Where you had a software architect, you had a product manager, you had basically these different roles, and they were all collaborating to create your code, right? So it's basically just trying to like create code given a description. But the roles that they chose and the number of agents in that system that they chose are based on kind of human software organizations. But I'm pretty sure that that's not the optimal way to do it, right? Human software organizations are organized in such a way more due to the kind of nuances of kind of like human bureaucracies and kind of like legacy hierarchies and stuff like that. I'm pretty sure that the optimal number of agents and the optimal roles for specific agents in something like writing code products is yet to be discovered. It might be the case that you have like a specific documentation only agent, and then you have a code only agent or something like that. I don't know, I'm kind of going down the rabbit hole here, but you have one brain running 4 unique agents. Yeah, Josh, this is kind of what I'm saying, is that the word agent is also kind of like losing its meaning, right? Because here in classic RL, the agent has a very specific meaning because it's like the actual, there's only one neural net, and the neural net is the policy, and or you can have another neural net for the value function, but normally there's just one. In model-free RL, you just have the neural net that is the policy, and the policy takes actions, and that's it. So there's one agent, right? But in these, now we're seeing these systems where you have multiple agents, but they're all kind of within a bucket, so it's kind of like a hive mind, right? So I could see a world where the Optimus robot, right? Optimus robot, or actually, let's not give Tesla more publicity. Let's do the Digit robot, which, by the way, guys, if you guys haven't heard about it, this Digit robot, they're making a huge factory for it. So I think we had a bet going on our Discord channel about how soon we get to full general purpose humanoids, and I said it's less than 5 years. I think in 5 years we might have these things in your house because they're really not that expensive. But when you have this thing in your house and it's going around and it's just like picking things up in your house and doing that, like, you think of it as one agent, but it might actually be inside of it there's like 10 different LLMs, right? There might be an LLM for each arm. There might be an LLM that does the vision part. I don't know what it looks like inside, right? Like, there's kind of it's what I'm saying. It's like we're in an entirely new green field of reinforcement learning where it's like, what do these multi-agent systems look like? Do you have 100 agents? Is it 1,000 agents? 1,000 agents seems like it's coordinating that is just way too much overhead. So there's probably some optimal size. Maybe it's 10. Maybe it is just one, right? Maybe you just have one agent that does everything. So I don't know. And then you as a human probably only want to see it as a single individual agent. You probably don't want to feel like you're talking to 10 different personalities within your robot. You probably want to feel like you're just talking to one personality. So there's probably an agent that's specifically meant to be the communication agent that communicates to you, the human, and has like a kind of like a specific personality that's consistent through time, but that's only one facet of all the different agents that are running inside this robot. So I don't know, guys. The future is very exciting. Perception with the robot. Here they're even using the word robot. Manipulated variables. We use a within subject. In particular, every user tries to finish the task by himself or collaborates with different numbers of robots with varying degrees of competencies. We randomize the order of treatment. Participants work on the task by themselves. So here's different kind of different experiments that they ran where they had their 12 subjects play with these 2 females and 10 males. Unfortunately, this is the reality of engineering. Just a lot of dudes. But, I think it's getting better. Collaboration score. Human alone, 1 agent plus human, 2 agents plus human, 3 agents plus human. So there does seem to be the more agents and you have, the better the success rate is. So human with more agents is better than... Actually, maybe not. Perceived enjoyment. Humans enjoy the game more if they collaborate with the right number of agents. And this is kind of what I'm saying, right? Where maybe as a human, you want to feel like you have one best friend, right? Maybe there's some humans that they don't want to feel like their AI kind of agent or counterpart that's doing stuff for them is like 100 different people. So maybe there's this kind of like humans want to feel like they have one best friend, even if that one best friend is really a hive mind of 100 different agents that are constantly changing. So, damn, dude, that's a whole other dimension now of like, okay, there's an optimal amount of agents to complete a specific task, but then there's an optimal amount of agents in terms of what is the human preference there. Do you want to feel like you're playing a video game with 2 other AIs? That sounds fun, but do you want to feel like you're playing a video game with 100 other AIs? that doesn't sound that fun anymore, right? Like, would you want to play Minecraft and you're just one of like 1,000 different different agents in that Minecraft world? That sounds kind of lame, right? It's like there's a kind of like an optimal amount there. And most video games and team sports actually do this as well, right? Where it's like 5 kind of seems like an optimal number. A lot of team sports and video games kind of center around this like kind of low single digits. So like 3, 4, 5 people, right? You don't see a lot of sports where there's like 100 people on a team, or you don't see a lot of video games where you're on a team with 100 people, right? Because it's like there's that, I forget what it's called, but there's like a specific, I think it's called Dunbar number. Yeah, where basically, because we kind of come from primates, we have like a specific number of humans at which point, or agents at which point, it's a kind of beyond our comprehension. It's like it's very difficult for us to like interact with more than a certain number of people. This is a nice little graphic here. So maybe we see that same kind of thing in these multi-agent systems where even though there's more agents, a lot of them are actually hidden from the human because the human has a limited brain capacity and doesn't want to feel like they're interacting with 100 different agents. Perceived assisting. No significant difference in terms of human perceptions of helpfulness while collaborating with more agents. Perceived bendability. When collaborating with more agents, players depend on the agents more. So this is kind of more along the line that I'm saying. Like if you're in a game with 100 other agents, you kind of feel like you don't have to do anything. You probably just sit around, you're like, hey, they'll do it for me. But if it's just you and one other AI, it feels more collaborative because it feels like you're kind of, it's a 50-50, right? So maybe the kind of, when you're sitting there in that Google inbox of the future, you want to feel like you have some impact, right? Versus like if you're just one of 100 different things, it feels like you have no impact. And humans want to feel like they have impact. Humans want to feel like they're actually doing something. They want to feel like the actions that they take are actually causing a change in the world. So maybe the AIs will have to account for that and make sure that the human feels like it's doing something. There is no... what does this even mean? Oh, I see what's wrong. It's like formatted weird. Players think collaborating with AI agents will improve productivity. There is no difference in terms of what trust when collaborating with more agents. Okay, so you don't need to have more or less agents to trust them. Either you trust them or you don't trust them. That kind of makes sense. And then collaborating will improve productivity. I think most people would agree with that. Even though the success rate is generally higher, there is no significant effect compared with collaborating with one agent, collaborating with 2 agents, or collaborating with 3 agents. Playing with intelligent agents, human players will take their actions based on other players' actions. Human players also found that intelligent agents are more predictable compared with random agents. Seems pretty standard. I mean, if you have random agents that are just kind of taking random actions, you're going to pretty quickly be like, that agent over there seems to be doing some weird shit, you know? Visualizing Cuisine World. Okay, so here you have some visuals. Seems like some people played this in kind of a top-down world, and then some people played this in a VR way. Okay. Study on prompt components. Okay, this is kind of more interesting here. So they're going to go into the actual prompt and see which part of the prompts are more important. We excluded individual components like inference knowledge, reduced the prompt example to a mere 2 steps instead of the complete demonstration, and evaluated the model without environment feedback. For context, our principal experiments, varying in the number of agents, incorporate one-shot examples of the corresponding number of agents. A significant drop in performance is observed when environment feedback is excluded. Yeah, I mean, that seems pretty obvious. Replaying action sequences reveals that without feedback tends to repeat mistakes and gets stuck in specific states for prolonged durations. Another key is that succinct 2-step demonstrations of input-output can still achieve commendable performance for unseen tasks. Notably, these 2 steps, there's no explicit guide to finish any task. We observe that integrating human-crafted inference knowledge bolsters the LLM's dispatcher performance. So this is the hints, right? So inside the prompt that you're giving it, you're not just saying, here's what you need to do, here's the task, here's the previous actions, here's the previous observations, and go, right? You're actually giving it some little hints, some human-crafted knowledge. And this makes sense because even as humans, we do this, right? So if you're starting a new job, the person who like introduces you is like, hey, here's some helpful hints. Like, oh, if you have a question about this, go do that. If you are doing this, here's a little hint for that. So it's weird that that same type of stuff works with these language models, because IMO dealing with these language models is almost more like psychology than it is like engineering. Emergent collaboration task understanding. Full few shot demo refers to a comprehensive demonstration of a task detailing each step and procedure. In contrast, we use provided GPT-4 with only a partial demonstration or a glimpse of the task. Okay, so do you give it the entire demonstration of the task in this kind of API space where it's like, agent 1 go to here, then pick up this, then put it here, then do that, then put it. So it's like, do you give it the exact example? So let's see that. Where is the with few step? 8 out of 26. That actually seems worse. It somehow got worse. What the fuck? This is weird. So it doesn't actually seem like it matters that much. Huh. Okay, so it actually doesn't matter. You don't need to give it a full example, a demonstration of the exact procedure. It seems to kind of be able to just infer, but this is limited by the environment, right? This is like within the specific cooking environment, and there's plenty of cooking text on the internet, so it kind of already knows how to make sashimi, right? It's kind of weird to think about it, but even though it's playing this game and has never played this game before, and if you ask it to make sashimi, it's like, oh, okay, I need to go cut the tuna, right? It already kind of knows just from reading the internet a million times that in order to make this thing, you need to cut the tuna. So maybe that's why the few step doesn't matter as much. It doesn't seem to matter. So this is the ablation study. This is without the inference knowledge. So the inference knowledge is the tips. So it seems to do a little bit worse. So 0.76 versus 0.71. And then without the feedback. So this is without telling it you're doing a good job or you're doing a bad job. That seems to be the most important. Okay. Interesting. So few step and inference knowledge don't matter that much, but feedback does matter a lot. 0.311 task completion versus 0.76. Here we go. Claude versus Llama versus ChatGPT. What do we got? 0.68, 0.32, and Llama does 0? What? What is it? What? It just, they don't even try? The fuck? What's the point of having Llama here if it literally just does 0? That doesn't make any sense. 0.82, 0.37, 0, 0.84, 0.43, 0. Damn, dude. ChatGPT and Llama literally just can't do this at all? It's only GPT-4 and Claude? Shit. Okay. Don't need to tell me twice. What do we got here? More different number of agents. Okay. That's not that interesting. And then I guess they bring it to Minecraft. Okay, so now they're basically doing the same thing, but with Minecraft. And conclusion. In this paper, we presented MindAgent, an infrastructure for multi-agent collaboration through LLMs across multiple gaming domains. We investigated the multi-agent planning capabilities of MindAgent, and we deployed our infrastructure into real-world video games to demonstrate its effectiveness for multi-agent collaboration and human AI collaboration. Beyond its practical applications, we hope that our endeavor serves as a beacon guiding the development of future gaming systems where human AI collaboration is seamless and intuitive. And it's not even just gaming. I think that this might be like a controversial opinion, but I feel like every single software, everything in the future is going to be this, right? Like we're going to move away from this paradigm where we're designing algorithms that are specific to specific applications and tasks, and we have kind of different things, right? You have like robot software is a completely different beast from accounting software, and it's a completely different beast from the software that you use to run something else, you know? But I think we're moving into this world where the fundamental unit of compute is just going to be a language model. It's just like everything is just going to be language models talking to other language models, and then that's it. So maybe every single robot, every single, even your accounting software, all of those end up looking more and more similar because they're just a bunch of little LLMs talking to each other. And that's kind of a crazy world to think about, but I feel like that's where we're headed, right? because we now have this piece, we now have language models, which are, I'm not afraid to say it, but language models are AGI, right? People are afraid to say that. People have moved the goalpost, but you can't have these kind of papers. You can't be doing this kind of shit without AGI. Like, you know what I'm saying? Like, let's get real here. Like, this is fucking crazy. Where you have these AIs that are basically just interacting. They like don't know anything about this cooking game, and they can like coordinate and play this cooking game. Like, come on, this is AGI. And the reason that we're able to do this crazy stuff, and the reason that we're now moving into this new paradigm where it's like, okay, you just have this fundamental unit of compute, which is the language model, and then how do you coordinate these language models? And it's kind of like this entirely new branch of reinforcement learning. I don't know. I'm excited about it. And there's going to be sticklers. There's going to be sticklers that are like, hey, this isn't real reinforcement learning. Real reinforcement learning has this MDP. This isn't actually AGI. It needs to be embodied in order to have AGI. Like, miss me with that. I feel like we're already there. Optimistic, our insights and findings might catalyze innovations in crafting games that are not only technologically advanced, but also significantly more engaging and enjoyable. Yeah, that's what we're going to spend our future doing, is playing VR video games with AGIs. Cool. So we have some time here. So we created AGI priors. Exactly. It's like literally any problem can just be turned into a large language model version of it. Like, describe any problem to me, and I will describe to you a multi-agent LLM system that is better at solving that problem than whatever current algorithms you're using and current software and current situation you're using to solve that. Okay. So with the time that we have left, let's kind of scroll through this survey paper. So I obviously went over this paper. This paper is not going to be as cool as the kind of survey paper, but the survey paper is going to be way too long to read on a stream. But, you know, these survey papers are nice because they have these little tables here so you can actually click. So if you're interested in one specific aspect, you can go here. You can be like, oh, memory. Okay, let's look at the memory. Let's see if they mention the stuff that we were talking about with the selectively picking the right memory. Memory mechanisms necessitate specific memory mechanisms to ensure proficient handling of things. Okay, I agree with that. Yeah, as agents amass a vast array of historical observations and action sequences, they grapple with an escalating memory burden. Right, so how do you deal with that? Well, you could just get a bigger context, which we kind of came to that same conclusion. You could compress it even more, so you can say, okay, well, here's a year worth of experience. I'm going to compress that into like just a couple sentences, so my total amount of memory is still something that I can feed into the context. You could compress memories. Here you have your vector databases. Memory retrieval. I feel like this is kind of more the solution. To me, it's going to be like this kind of like hierarchy of memory where you have kind of super cold storage where everything is stored. Then you have kind of a more immediate cache, and then you have kind of like this hierarchy of caches that are closer and closer. Something like that. Let's see, what else? Reasoning and planning, transferability. Let's read something a little crazy here. Social behavior. Behavior and personality. The agent society represents a complex system comprising individual and group social activities. LLM-based agents have exhibited spontaneous social behaviors in an environment where both cooperation and competition coexist. Yeah, these language models are basically humans. You know, sometimes people call it an alien intelligence. Like, I've heard that in a bunch of different podcasts where they're like, oh, AI is like an alien intelligence that we can't understand. But I don't think that's correct. I think that AIs are trained on human data. So large language models are much more human than people think they are. Like, they're going to have a lot of the same flaws. They're going to come up with the same conclusions. Like, I think language models are more like humans than they are like some kind of alien. Right? So that's a good thing and a bad thing, because the good thing is that, okay, we already know how to deal with humans. Like, we have thousands of years of kind of all these different ways of coordinating humans together and making sure that humans don't do bad things. But the bad thing is that all the messed up things that humans do, language models are going to be doing the same shit. Unless you can somehow control them, but the mechanism of control would just be worse than the negative externality of having that control. I don't know what I'm trying to say there. Simulated agent society. You have an environment, individual has some personality. You have a group of individuals. Here's your human. I don't exactly know what they're trying to do here. An individual level, agent exhibits internalizing behaviors like planning, reasoning, and reflection. It also displays intrinsic personality traits involving cognition, emotion, and character. And personality is emergent, right? As any language model creates its own context, that context is the personality, right? So it's like personality emerges from consciousness, if you want to think of it that way. Like just the fact that you are doing things and receiving and perceiving things, the collective history that you've perceived, that is your personality. So any agent is going to have slightly different histories, and those slightly different histories means that they're going to have slightly different personalities. An agent and other agents can form groups and exhibit group behaviors. Whether virtual or physical contains human actors and all available resources. In human society, strong personal values vary widely and tend towards individualism and competitiveness. In contrast, LLMs, which are designed with an emphasis on being helpful, honest, and harmless, often demonstrate a tendency toward neutrality. That's one way that we could do the safety thing, which is basically just always have something in the prompt which makes these LLMs helpful, honest, and harmless. The alignment with neutral values leads to conformity behaviors, including mimicry, spectating, and reluctant to oppose majority. Yeah, this is kind of the psychology stuff coming up again, where it's like, again, because these language models are more human-like than we think they are, they kind of have a lot of the same outputs, right? Where basically, if you make them helpful, honest, and harmless, they end up basically mimicking most of what you do. They kind of tend to be observers, so they'll spectate rather than take action. And then if a bunch of people want to do one thing, they're not going to oppose that thing. So all the stuff that applies to humans applies to language models. Negative group behaviors can undermine the effectiveness and the coherence of an agent group. Conflict and disagreement arising from heated debates or disputes among agents may lead to internal tensions. What? Recent studies have revealed that agents may exhibit confrontational actions and even resort to destructive behaviors, such as destroying other agents or the environment in pursuit of efficiency gains. Ooh. Glimpses of human-like intelligence. Just as human personality emerges through socialization, agents also exhibit a form of personality that develops through interactions with the group and the environment. I would say that's literally the definition of personality, is that your specific interactions with an environment and with yourself in your head, right? Because as a human, you're kind of constantly creating your own context. You have thoughts, and then those thoughts are becoming memories, which then are used to prompt your next thoughts, right? So it's like you have your own kind of history that you're building in your head, your own narrative of like who you are and what you do and what you're telling yourself who you are, and that kind of reinforces on itself. And when you look at a human and a human has a specific personality, that personality is just a result of that. So LLMs are going to have the same thing. So if you have an LLM that maybe it's taught to be critical, right? Maybe within your little software engineering organization with different LLMs acting as different people, one of the LLMs is told that it needs to be critical, right? It's maybe the pull request feedback LLM, and it gives you feedback on your pull requests. And inside the memory, inside the context, inside the chain of thought of that language model, it's constantly just negative, like toxic, like this is bad, this is bad, this is bad, this is bad, this is bad. And it's like that LLM over time is going to develop this personality of just being very critical, very negative all the time. And what happens when you have LLMs like that are very, very critical? Do they become ostracized from these LLM societies? Like, do they kind of spiral into this destructive behavior and eventually try to destroy the other agents? Like, I don't know, a lot of questions that we need to find answers to. LLM-based agents are now demonstrating not only sophisticated reasoning, but also a nuanced understanding of emotions. Again, I just feel like language models are more human than we give them credit for. So there's a huge amount, like any text that humans write has emotional undertones. So all the text on the internet has some kind of emotional undertone, which means that language models are going to pick up on that the same way that they pick up on kind of the fact that a table is a thing. You can put things on top of tables. They're picking up the same kind of semantic understanding of like emotions, right? So they understand that you can be angry, and if you're angry, you're going to do these things, and they can understand that you can be sad, and if you're sad, you can do these things. So I think LLMs are going to be emotional. They're not computers of the decades prior, which are kind of just like cold and calculated, like a calculator, right? A calculator has no emotions, but a language model does. All right, what else do we got here? Personality, physical environment, virtual sandbox, ethical and social risks, open problems. Let's see. The debate over whether LLM-based agents present a potential path to AGI. Artificial general intelligence, also known as strong AI, has been the ultimate pursuit of humanity in the field of artificial intelligence. I would say that we're basically already there. The fact that we're literally creating these multi-agent systems, to me, is indicative that we have the fundamental building block, which is a general, flexible intelligence that can zero shot to new types of tasks really easily. And that is literally what language models are. So I would say we're already there. Narrow AI is typically designed for specific tasks. Highly debated. Given the breadth and depth of GPT-4, some researchers believe that large language models can serve as early versions of AGI systems. I 100% agree with that. The main support lies in the idea that as long as they can be trained on a sufficiently large and diverse set of data, LLM-based agents can develop AGI capabilities. Is that the act of autoregressive language models itself brings about compression and generalization abilities, just as humans have emerged with various peculiar and complex phenomena during their survival. Language models, in the process of simply predicting the next token, can achieve an understanding of the world and reasoning ability. Agree with that. Let's read the negative case. So here are the people that don't agree with me. Believes that constructing agents cannot develop true strong AI. Their primary argument centers around the notion that LLMs, relying on autoregressive next token prediction — this is the pre-training task that large language models are trained on, right? They just predict the next token in a sentence or the next word — cannot generate genuine intelligence because they do not simulate the true human thought process. That seems bogus to me. Merely provide reactive responses. LLMs do not learn how the world operates by observing or experiencing it, leading to many foolish mistakes. They contend that a more advanced modeling approach, such as a world model, is necessary to develop AGI. Isn't a world model exactly the understanding of the world and reasoning ability that comes out of next token prediction? That's what I would say. We cannot definitively determine which viewpoint is correct until true AGI is achieved. Here's the goalpost moving that I'm talking about, where, okay, now they just moved the goalpost even further. Here's the physical environment. So this is when people talk about embodiment, right? They say that AGI isn't going to be AGI until it is embodied. Kind of what they're referring to is that you got to put it inside a robot. It's got to be able to see the world and touch the world and interact with the world, and that's how you're going to get AGI. I would just call that embodied AGI. They not only need to understand and reason about ambiguous instructions, but also process the ability to learn and apply new skills. Flexibility. Collective intelligence. What magical trick drives our intelligence? The reality is there's no magic to it. As Marvin Minsky eloquently expressed in The Society of Mind, the power of intelligence originates from our immense diversity, not from any singular flawless principle. Often decisions made by an individual may lack the precision seen in decisions formed by the majority, right? The hive mind is better than individual. Like the ant colony is more intelligent than the individual ant, which is kind of weird because a lot of people don't see the ant colony as an agent, but hive minds are an actual thing. It arises from the collaboration and competition amongst various entities. This intelligence manifests in bacteria, animals, and computer networks, appearing in various consistent-based decision-making patterns. Creating a society of agents does not necessarily guarantee the emergence of a collective intelligence with an increasing number of agents. Coordinating individual agents effectively is crucial to mitigate groupthink and individual cognitive biases, enabling cooperation and enhancing intellectual performance within the collection. By harnessing communication and evolution within an agent society, it becomes impossible to simulate the environment observed in biological societies, construct sociological experiments, and gain insights that could potentially advance human society. Yeah, so maybe one point here on collective intelligence is that a lot of times in podcasts, people think about what happens once you have this kind of artificial superintelligence, right? And how does the artificial superintelligence deal with humans? Does it destroy all the humans? Does it kind of fall into this paperclip maximization situation where it basically decides to destroy the humans? And I think that we don't need to imagine that scenario. It literally already exists, right? If you think of a company like Microsoft or a company like Google, those are basically artificial superintelligences. Right now, they're a entity that is really a hive mind composed of thousands of humans, but if you blur your eyes and you kind of put every single human that works at Microsoft inside a box and then saw that box as a single agent, as a single entity that took actions in the world, that's what an artificial superintelligence looks like. It looks like these giant megacorps, right? Or a nation state is another type of artificial superintelligence. A religion is another type of artificial superintelligence, right? These hive minds. And we don't live in a world where humans are the most important thing anymore. In fact, our world is more a world for hive minds, right? So in the United States, corporations are the ones in control. Humans aren't in control anymore. It's these corporations, these superintelligence, these hive minds, right? And the hive minds, they don't actually want to hurt the humans, right? Like Microsoft isn't hiring mercenaries that go out and kill the humans. Like that's not something that corporations do. They can hurt humans, but they hurt humans in ways that are very difficult to understand, right? They like kind of create inequality, and the inequality creates certain problems. And it's not, so I think that's going to be what happens in the future, is that these superintelligences, they're not going to actively harm humans. They're not going to actively hunt or kill humans or harvest you for your carbon and your energy. Like they're not going to give a shit about you. They're going to be interested in their own things, and then we're just going to be more left in the wayside, right? We're just going to be like the relationship between Microsoft, the company, and you, the human, is going to be the same type of relationship between an artificial superintelligence and you, a human. So it's not that they actively want to hurt you and hurt humans, it's that they basically don't care about humans. So, I don't know. We're already living in a future that is controlled by the hive minds and the artificial superintelligences. It's just that they're called corporations now, and that humans are operating within them. But over time, all those little different agents will be replaced, and eventually these giant corps, there's going to be no human that's in control of them anymore. They're basically just running themselves. So I don't know. I'll end on that note right there, because this is getting pretty deep pretty quick. So let me take a sip of this water. We'll summarize this paper, and then we'll end it here. All right. So today, we read the paper MindAgent, Emergent Gaming Interactions. This is a paper coming out of Microsoft, a couple different academic institutions as well. So basically in this paper, this is a continuation of the large language models as agents kind of thread that we've seen in the Voyager Minecraft paper. We also saw it in some of the robotics papers, where we're seeing that these large language models are so good at generalizing to any task and doing so in a zero-shot way that you can basically plug and play them into any system, and they work beautifully here. And in this particular paper, they plug and play them into these collaborative multi-agent games. So they have this little cooking game where you have to basically create these little recipes, and then they also have a kind of a Minecraft version of that cooking game, I guess. And in this paper, they kind of like dig into the the different aspects of that, right? What does it mean to have these agents interacting in this game, right? What does that system look like? How do you organize that system? So they have basically the environment. The environment has a state, and then you have a memory, an external memory that stores all the things that are happening. And then you have this kind of centralized dispatcher, which aggregates everything and then creates actions, which the what they call multi-agents take. So I wouldn't really classify this as a multi-agent system. To me, if this was a true multi-agent system, each of these individual agents would have their own memory and their own kind of internal thought process that would be represented by an LLM. So I see this more as kind of one agent kind of hive mind that has multiple hands, right? Where each of these NPCs are kind of like a hand. But this is just one example of what kind of like the future of these LLM agent systems look like. And another thing we kind of looked at today was this larger survey paper where they basically, this is just a survey paper of a bunch of other kind of LLM agent works. So you have everything from single agent, multi-agent, human agent cooperation. But this is to me, both of these are basically coming from the original formulation of reinforcement learning, which is this idea of a Markov decision process where you have an agent, an environment, the agent takes actions in the environment, receives state, or is observing some state and receiving some reward from the environment. And we're seeing basically this as the launching point for an entirely new branch of research and science, which is how do you use language models in these systems to basically do any task. And here you're seeing them for like little video games, but I think this works for any task you can think of. And I don't think this is the end-all be-all. I think that there's still a lot of things that are going to improve and change and adapt over time as we get better and better LLMs, as we get LLMs that have more context, right? Maybe this memory changes, right? Maybe you have separate memory caches. I think this is going to get more complicated before it gets more simple, but it's cool to see, because we're really seeing the birth of kind of a new type of reinforcement learning that is a step function improvement over previous types of reinforcement learning. And I can't wait to see kind of all the cool stuff that people build with these kind of multi-agent LLM systems. And again, I think it's beyond just video games and robotics. I think this is, I use this, the example of like accounting software, right? But even within like a Google Sheets, right? Maybe you have multiple agents there that are kind of helping you in different ways. And I don't know, pretty cool stuff. There's kind of some unnecessary mathematical equations there where they basically just describe that if you complete more tasks, you get a higher score. There doesn't really seem to be a strong relationship between the number of agents and the number and how well you can perform. I think part of that is because they have these aren't really individual agents. These are more like a single agent. I think if they would have had individual agents, each with their own memory and each with their own kind of internal chain of thought, kind of action deciding process, maybe you would have seen more interesting relationships there where the more people you have in the kitchen, the more difficult it is, or maybe it becomes easier. But the way it's formulated now, I don't think the number of agents is necessarily relevant, and there doesn't seem to be a strong relationship based on these graphs. What else? Another interesting thing that we saw here is actually that the prompt engineering still matters. So they thought, okay, maybe if we put tips into the system prompt, or if we show some examples in the system prompt, it'll lead to more task completion. That was not the case. But if you do give it feedback versus not give it feedback, that ends up having a huge difference in the performance. So the prompt engineering is still alive. And kind of another interesting thing here, Llama and ChatGPT being GPT 3.5, are somehow absolutely terrible compared to GPT-4 and Claude 2. I don't know if this is Llama 2. I'm pretty sure this is not, or else they would have said Llama 2, but maybe Llama 2 is better. I don't know. But that's it, guys. That's pretty much it. Little exploration into the agent world, into the agent verse. Yeah. Hope you guys find that interesting. Thanks, John. Thanks, Josh. Thanks, Bob. Thanks, Irabu. Thanks, Yujun, Luke, everybody else. Thanks for watching. And see you guys tomorrow. Tomorrow we're going to be reading a paper on language modeling is compression. It's kind of more of a math theory, kind of information theory paper. So different flavor. Definitely not going to be cute little cats and Minecraft, but maybe you're more into the math than the cute cats, you know? So see you guys later.